Dear students, our course is CE 303 Structural Analysis 2, Module 1 3-moment equation. Syllabus is Clapirons Theorem of 3-moment, Derivation of 3-moment equation, Application of 3-moment equation for the analysis of continuous beams under the effect of applied loads and uneven support settlement. What do you mean by continuous beam? A continuous beam is the one which has more than one span or more than two supports. That means that is a statically indeterminate beam. What do you mean by statically indeterminate beam? If all the unknowns cannot be solved by using the equations of equilibrium alone, that is known as statically indeterminate beam. If all the unknowns can be solved by using the equations of equilibrium alone, then that beam is known as statically determinate beam. If you are considering a continuous beam like this, subjected to an external loading, sagging moments occur in the middle of the region of the span and hogging moments occur over the supports. This hogging moment over the support, that means support moments, that can be determined by the application of Clapirons theorem of 3 moments. Next is derivation. This equation is applicable only for two consecutive spans of a continuous beam. So consider AB and BC are any two consecutive spans of a continuous beam subjected to an external loading. ME, MB, MC are the support moments at the supports A, B and C. Then the 3-moment equation is given by ME into L1 plus 2MB into L1 plus L2 plus MC into L2 is equal to 6A1 x1 bar by L1 plus 6A2 x2 bar by L2. In this, A1 is the area of the free bending moment diagram for the span AB. A2 is the area of the free bending moment diagram for the span BC. x1 bar is the centroidal distance of the free bending moment diagram on AB from A. x2 bar means it's a centroidal distance of the free bending moment diagram on BC from C. L1 is the span length of AB. L2 is the span length of BC. A1 dash is the area of the fixed bending moment diagram for the span AB, and A2 dash it is the area of the fixed bending moment diagram for the span BC. Notations are like the 1 indicates the span AB and 2 indicates the span BC. And this dash represents the case of fixed bending moment diagram. The free bending moment diagram means it is the bending moment diagram due to the applied loads, and the fixed bending moment diagram means it is the bending moment diagram due to the support moments. Then consider the continuous beam ABC with two consecutive span AB and BC, which is subjected to UDL as shown in this figure. Then consider the span AB first. Then along AB, consider a section at a distance of x from A. Mx is the free bending moment at this section and Mx dash is the free bending moment diagram at this section. So, the net bending moment is given by Mx minus Mx dash. So, we can write EA d square y by dx square is equal to Mx minus Mx dash. Multiplying by x on both the sides, EI x d square y by dx square is equal to mx into x minus mx dash into x. Then integrating this from 0 to L1, that means over the span AB. Then you will get like this. Then applying the boundary conditions. The boundary condition at x is equal to 0. At x is equal to 0 means the support A. At x is equal to 0, y is equal to 0. That is the first boundary condition. Then at x is equal to L1, the slope is equal to IBA. IBA means it is the slope at B for the span AB. At x is equal to L1, the slope dy by dx is equal to IBA and y is equal to 0 since the support B. The next boundary condition is degree 0 to L1 mx into x dx. That means the moment of the free bending moment diagram on AB about A. That can be represented as A1 x bar. Similarly, 0 to L1 mx dash x dx can be represented as A1 dash x1 bar dash. For the moment of the fixed bending moment diagram on AB about A, substituting all these values, then we will get EI into L1 IBA is equal to A1 x bar minus A1 bar x1 bar dash. Then A1 dash, that means area of the fixed bending moment diagram for the span AB. Area for the fixed bending moment diagram for the span AB. This is the shape of trapezium. Then area of that trapezium that will be given by MA plus MB into L1 by 2. The centroidal distance of this fixed bending moment diagram for the span AB from A, that is given by MA plus 2MB divided by MA plus MB into L1 by 3. That is the centroidal distance of the trapezium. Then substituting all these values, then we will get the equation number 1. Similarly, if you are considering the span BC and taking C as the origin, if you are considering the span BC and considering C as the origin, then we will get the equation number 2. This is the equation number 2. In the equation number 1, we are having IBA, and the equation number 2, we are having IBC. IBA means it's the moment at B for the span AB, and IBC means it is the moment at B for the span BC. IAB is marking towards left and IB is marking towards right. Okay, that means IBA is equal to IBC. That means IBA plus IBC is equal to 0. Then substituting this, then we will get finally the Clapirons theorem of 3 moment equation. Then for example, if you are considering this as the span, AB span, you subject it to UDL like this. This is the free bending moment diagram. As we know, the free bending moment diagram means it is the bending moment diagram due to the applied loads. So in order to draw the free bending moment diagram, firstly consider each span as a simply supported spans. Then consider the loads which are subjected on this span. Then consider the bending moment diagram as considering the beam as a simply supported one. In this case, the simply supported beam is subjected to UDL. That means the free bending moment diagram is a parabola with the value WL square by 8. Then what do you mean by A1? A1 means area of this parabola, that means 2 by 3 into base into altitude. And x1 bar means the centroidal distance of this free bending moment diagram. Since it is symmetrical, it will be L1 by 2. Now when you are substituting all these values, then we will get 6A1 x1 bar divided by L1 is equal to WL cube by 4. Moving on to the problem. Analyze the following continuous beam using Clapirons theorem of 3 moments method. EI is constant throughout the beam. This is the given question. AB is subjected to UDL of 5 kN per meter over the span length 4 meter and BC is subjected to an eccentric point load of 20 kN at a distance of 2 meter from C. The first step is draw the fixed free bending moment diagram. In order to draw the free bending moment diagram, consider each span as a simply supported beam. Then consider AB as a simply supported beam subjected to UDL all over the length. That means the bending moment diagram is a parabola with the value WL square by 8. That is equal to 10. Then similarly, along BC, it is also consider it as a simply supported one and is subjected to an eccentric point load of 20 kN from 2 meter from C. So the free bending moment diagram is a triangle with the value W A B by L. In this free bending moment diagram, x1 bar is measured from A and x2 bar is measured from C. The equation is L plus B by 3. Then first step is consider A, B, C. The three moment equation is applicable only for two consecutive span. So you can consider A, B, C. In this A, B, C, write the three moment equation. In the three moment equation, as you know, L1 is equal to 4 meter and L2 is equal to 5 meter. For L1 it means it's a span length of AB and L2 means span length of BC. That is L1 is 4 meter and L2 is 5 meter. Then A1 means it is the area of the free bending moment diagram over the span AB. That means area of this parabola. That is 2 by 3 into base into altitude. That value is 26.67. 2 by 3 into base into altitude. That is 26.67. Since the free bending moment diagram over the span AB is a symmetrical one, for x1 bar means it's 2 meter, that means middle of the span AB. x1 bar is 2 meter. x2 bar means it is the centroidal of the free bending moment diagram over the span BC from C. From C, the equation is L plus B by 3, that means 2.33. A2 means it is the area of the free bending moment diagram over the span BC. That is a triangle. The equation for area is half BH, half into B's base, that means half into 5 into 24. That is 60 meter square. Then in this equation, L1 you got, L2 you got, A1, x1 bar, all these values you know. Then out of this equation, MA, since A is the hinge support, that means the moment at A is equal to 0. Then C is the hinge support, that means moment at C is also is equal to 0. That means the only unknown is B. Substitute all these values and find out the value of MB. That MB is 13.765 kilonewton meter. Then draw the bending moment diagram. This is the free bending moment diagram. Then fixed bending moment diagram means MA is equal to 0, MB is equal to 13.765 and MC is equal to 0. Join these values, that is the fixed bending moment diagram. This is the combined bending moment diagram. That means combining the free bending moment diagram and the fixed bending moment diagram. The portion belongs to free bending moment diagram, that will be plus, and the portion belongs to the fixed bending moment diagram. After combining free bending moment diagram and the fixed bending moment diagram, the portion belongs to the free bending moment diagram, that is positive, and the portion belongs to the fixed bending moment diagram, that belongs to negative. This is the combined bending moment diagram. Then next is the shear force diagram. In order to draw the shear force diagram, firstly we have to consider the support reaction. For calculating the support reaction, consider each span separately. Consider AB and BC separately as a simply supported beam. Mark all the reactions RA. Then B can be split into two, RB1 and RB2 and RC. Then mark all the external loads, that means 5 kilonewton per meter over the span 4 meter and 20 kilonewton at a distance of 2 meter from C. And mark the obtained value of MB 13.765. This 13.76 has to be marked in the clockwise direction if it is at the right support, and in the anti-clockwise direction if it is at the left support. In the case of AB, it is at the right support. That means you have to mark in the clockwise direction. In the case of BC, it has to be marked in the left support. That means you have to mark in the anti-clockwise direction. After marking all these things, apply the equations of equilibrium in order to find out the reactions Ra, Rb1, Rb2 and Rc. After getting the value of Ra, Rb and Rc, we can draw the shear force diagram as all the upward force mark in the upward direction and all the downward force mark in the downward direction. That means at the joint A, the first load is 6.56, that is acting in the upward direction. Then over the span AB, 5 into 4, 20 kilonewton is acting in the downward direction. Then when it acts in the downward direction at each point, it will be like this. After covering this, that means it has covered 6.56. Then balance value is 5 into 4, that is 20 minus 6.56, that is 13.4. That means the total 20 is acting in the downward direction. Then at the joint B, RB1 is 13.44. That is also acting in the upward direction. RB2 is 10.75. Like 13.44 in the upward direction. At this point itself, 10.75 is in the upward direction. Then there is no load from up to here. At this point, 20 kilonewton is acting in the downward direction. After covering at this distance, that means 10.753 is covered. The remaining value of 20 is 20 minus 10.753, that is 9.23. Then here there is no load at this point of C. At the point of C, there is RC that is acting in the upward direction. So mark in the upward direction RC of 9.25. This is the shear force diagram. And moving on to the next problem, analyze the continuous beam shown in figure. This is the beam. The loads are 18 kilonewton, 16 kilonewton and 3 kilonewton per meter over the span of 4 meters. Then as I said, the first step is free bending moment diagram. First one, consider each spans as a simply supported beam separately and draw the free bending moment diagram, that is the bending moment diagram due to the applied loads. For the first span, it is subjected to 18 kilonewton at a distance of 4 meter from the left support. That means it is an eccentric point load. If a simply supported beam is subjected to an eccentric point load, that the free bending moment diagram is a triangle with the value WAB by L. The second beam, it is subjected to a central point load. That means it is a triangle with the value WL by 4. The third span is subjected to UDL. That means that is a parabola with the maximum value WL square by 8. Okay. Then apply the three moment equation. The three moment equation can be applied only for two consecutive spans. So we have to consider these spans A, B, C initially and then B, C, D as the second step. Then firstly consider A, B, C and write the three moment equation. Then in this three moment equation, we know MA is equal to 0. MA is equal to 0. L1 is equal to, we are considering A, B, C. L1 is equal to 6 meter and L2 is equal to 4 meter. MA is equal to 0. Then A1 means area of the free bending moment diagram over the span AB. That means area of this triangle. That is half into B into H. Half into 6 into 24. Then A2 means the area of the second triangle. That means half into 4 into 16. The next value is x1 bar. That means the centroidal distance of the free bending moment diagram for the span AB. That means at this distance, that is L plus A by 3. Then for the second span, since it is symmetrical, centroidal distance will be at the middle point. Therefore, A2, x1 bar and x2 bar. Okay. The next is substitute all these values, then you will get the equation number 1. Then the second case, consider B, C, D. When you consider BCD, write the three-moment equation. In this equation, we know the value MD is equal to 0. We are considering BCD. That means this span is considered as 1 and this span is considered as 2. Therefore, L1 is 4 meter and L2 is 4 meter. A1 means area of this triangle and A2 means area of this parabola. X1 bar means it is a centroid distance from the left support, that means from B, and X2 bar means centroid distance from D. Then substituting all the values, then we will get the equation number 2. By solving equation number 1 and 2, we will get the moment MB and MC like 15.78 and 5.06. Then 15.78 and 5 point something. Join these values, then we will get the fixed bending moment diagram. Combine this free bending moment diagram and the fixed bending moment diagram in order to get the combined bending moment diagram. Then draw the shear force diagram. When we draw the shear force diagram, consider the support reactions RA, RB1, RB2, RC1, RC2 and RC and all. Then consider all the external loads and consider the moments. Then apply the equations of equilibrium in order to find out all these reactions and mark all the upward forces in the upward direction and all the downward forces in the downward direction. That means this is your shear force diagram. Okay, thank you.